Well, hello class. Here we are, Friday, as we are talking about lesson two. We will get through this entire lesson today, and you should have time at the end to do homework. Um, the only thing that you guys don't know is that I recorded this video once already, and realized that when recording the video on the second monitor, the video didn't show any of the work that I've already done. So here goes. Take two. We are going to talk about power functions and modeling. Now, you might be wondering, oh no, not another function. But the nice thing about these power functions is that these are the building blocks, as well as we'll be talking about monomial functions. These are the building blocks for both polynomials and therefore rational functions. So what we will talk about today will connect to the rest of the chapter as well. So when we define a power function, it will look something like this: k times x to the n. Now that k is called the constant of variation. Now, there are going to be instances where in the past we've seen that this is also called like direct variation or inverse variation when we're dividing by that x. When we divide by the x, that's when the n is negative, which, as we think about this power, the n only rule for power functions is that it is a non-zero. Okay, so again, it'd be any negative number, any positive number. It just cannot be zero. It is from this power function that we will also learn today about monomial functions. Okay. This is where n is positive and it is, that's what that little symbol is the bolded z represents integer. So our monomial function is like a 1, like an x to the first, x to the second, x to the third. This would be like that leading coefficient at the beginning of any kind of polynomial that we see. So what we're going to do today is we are going to do some graphing of basic power and monomial functions. And we're also going to learn what properties we need to list when talking about analyzing a function. We will do that here in our first example. For f of x that equals 3 cube root of x, state the constant of variation find the graph and analyze the function. Okay. So, as we take a look at this function, the first thing that we should notice is that there's really no power there that we can see. But one thing that we should remember is that any radical function, whether it is like the square root function or the cube root function or the fourth root function, is that we can write those radicals as rational exponents. So here we should see that f of x is the same thing as 3 cube root of x. Okay. Next, we need to identify the constant of variation and the power. Wow, I wrote the same thing twice. I meant to write 3 times x to the 1/3. Remember, that radical number becomes the denominator of the rational exponent, okay? So the 3 is the constant of variation, and the 1/3 is the power. Always that number in the exponent. So this graph, and we can sketch these using our calculators, is going to look like this. Okay? This is an inverse of a cubic function. Okay? So like the point out here at 8 is going to be 6. Likewise, at -8, it is going to be -6. We can kind of plug in some of those numbers so that we can get kind of a good shape to the graph. So now, when it talks about analyzing the function, there are 6 properties that we're going to want to list. These are properties that come with us from chapter 1. We see them here in chapter 2. We'll also see them in chapter 3. The first one, for any function, we can find its domain, which is all real numbers, and its range, okay, which is also all real numbers. The next thing that we look at is the continuity. The nice thing is, on this function, there are no holes, there are no holes, and there are no vertical asymptotes. So it is continuous on the domain. 3. The next thing we look for is the slope. Where is the graph increasing and decreasing? Increase, decrease. Now, as we take a look at this, the slope at every point is positive. So it is increasing from -infinity to +infinity, all the way across. Number 4, the extreme values. Remember, extreme values are the same thing as maximums and minimums. This graph has none because it is increasing on the entire domain. Maximums and minimums only happen when it switches from increasing to decreasing. None. Because, we'll just use BC, the graph always increases. Okay? Number 5, the asymptotes. This has none, but we will see later in this chapter that rational functions in next chapter, as we deal with exponential and logarithmic functions, do have asymptotes. And then number 6, the end behavior. Remember, end behavior is asking what is happening when x is approaching -infinity and +infinity. Okay? Lucky for us, this is relatively straightforward. When x is approaching -infinity of f of x, it is also -infinity. The arrow on the graph is pointing down. as x approaches infinity of f, it is infinity. It is pointing up. Okay? So whenever there's a problem, starting now and moving forward, that's talking about analyzing the function, you're using these 6 properties. There are a couple of other properties that we could use, but we skip those because reflection is not important, and neither is whether a graph is bounded, like between 2 horizontal asymptotes. So there is one function that does that. It's called a logistic function that is covered in chapter 3, but we do not need to worry about that one. Now, the next example that we're going to look at is really just a transformation problem. It's just worded a little bit differently, okay? If f of x is negative 1/2 x to the third, describe the transformations and graph f. Okay. All right. So, 2 things are happening with this function. The first thing that is happening is the x-axis reflection. Okay, that's what the negative is for. And then there is a vertical shrink of 1/2. So as we graph this, if this is 8 up here and this is negative 8, let's graph this function. Still point at 0, 0. Negative 1/2 times 1 to the third is still negative 1/2. So it is going to be, wait, that's negative, negative, oh, positive. So it's going to be right about there. 2 to the third is 8. 8 times negative 1/2, negative 8 times negative 1/2 is negative 4. 2, 4. So then it's going to reflect over here. The one thing I realized I've forgotten to say is that in the homework, if it asks if a graph is even or odd, look at the exponent. This is an odd function. It is because it reflects over the origin. Okay? It reflects over the origin. If it is an even power, it is an even function. That shows its y-axis reflection, so that the left-hand side looks the same as the right-hand side, like quadratic functions or x to the 4th functions. Okay, so here we are. We've got an example of how we can apply the monomial function using our transformations. This is some stuff that we could have already done back in chapter 1. So this is a little bit of review already, knowing that we've covered that part of the content. Now, in our last example, we are going to learn how we can model using a power function. Okay. Example 3. Model the velocity of a rubber ball against the traveled distance. Then find the velocity at 1.36 meters. All right. So, as we take a look at this, we are going to have a table that will always be given to us. So, if D is our distance, we're going to have 4 distances in meters, I will say. Right there, it's meters. So 0.043, 0.161, 0.5, 0.3, 0.351, 0.594, and then our velocity, which is going to be meters per second, is 0.824, 1.711, 2.459, 3.052. So here is our data table. Now, what we're going to do here in the really the first big chunk of this, we're using that calculator. We are going to the stat button. We are going to the edit, and we are typing in the data. Now the data is already there because this is take 2 of the video if you have forgotten. So we type in the data points, how many, no matter how many there are. Here we have 4. You could have maybe up to 10 data points. Just depends on the problem. So what we are going to do is find a power model for this function. Okay. Model the velocity of the ball travel against distance. So we're going to do a power function, or we could say power model, power function. And to do this, it will be stat calc a PWR regression. Okay. Stat calc A is towards the bottom. It's after 0. And we enter and we get our model that has a pretty good correlation, might I add. It is V of D, because velocity, depending upon the distance, is 4.099, or you could put 4.1 x to the 0.502. Now the thing that's unique about this is that we could round this to 4.1 and understand that this is the square root of x. Okay. So here is our model, really that first line. So we're trying to find V of 1.36. So it's 4.099 times 1.36, 0.5 to the 0.502, 02, and this equals 4.78 meters a second. So we can take real world data and not just create like linear and quadratic and other kind of polynomial models, but also power models that have decimals as their exponents. That's the nice thing about these. It does its best job to essentially connect the dots. Okay, so you have about a handful of homework problems, 28 through 36 even. These are going to be like the first two problems. The first two problems, you are going to state the constant of variation, the power, graph it, and then analyze it. In the next three problems, you're just identifying the transformations. And then 49, 55, and 57, these are all modeling problems. 49, you're just given a table, you practice, and then you're given some context in 55 and 57. This is page 177 and 178. We will go over lesson 1 homework and this homework on Monday. I hope you all have a good rest of your day and have a good weekend. Bye.